Okay, so let's start building, let's start developing our linear time algorithm for finding all the strongly connected components in a graph. And specifically, we are going to go over an algorithm known as the Kosaraju Sharir algorithm. Okay, so the history of this algorithm is a little entertaining. I'll leave that for you guys to look up on Wikipedia. But let's start off with defining our problem. And our problem is that we're given a graph, GVG, that's comprised of some vertices and some edges, and we want to output all the strongly connected components. Okay, so last time in lecture, we came up with a straightforward algorithm. We had a way to identify the strongly connected component, that contains a vertex u. Okay, and how do we do that? We simply calculated the reach of u, i.e. all the vertices that u can reach, and then we use the reverse graph to calculate all the vertices that can reach u. Okay, so taking the intersection of these two calculations gives us the strongly connected component, because again, the strongly connected component is simply the set of vertices that can always reach each other. Okay, so if there is a vertex that can always reach another vertex, and that vertex can always reach you, then that vertex can also always reach other vertices that are in the strongly connected component, and those vertices can also reach that. Okay? Okay, so this is how we calculated a strongly connected component. It was a very efficient O of n time algorithm. And then to calculate all the strongly connected components, what do? We simply just did it for all values of u, right? So the question is, this is a good polynomial time algorithm, but can we do better? That's always a question in algorithms. Could we do a little better? And so let's look at our problem again, and let's look at the metagraph. And let's realize one thing about the metagraph is that the metagraph is created by collapsing every strongly connected component into a single vertex. Okay, so if we collapse every strongly connected component into a single vertex, then what do? Then we have a new graph, and this new graph is a directed acyclic graph, like we mentioned before. Okay, and so now that this new graph is a directed acyclic graph, let's try to think about why it takes polynomial time to calculate the strongly connected components in our straightforward algorithm. And that's because if we choose a vertex at random, right? If we choose, for instance, vertex A, and we want to calculate the SCC of vertex A, the first thing we do is run DFS on A, right? So if we run DFS on A, we end up visiting A and C and D and H and G, and also B and E and F. So if we run DFS on vertex A, we end up visiting every single vertex in the strongly connected meta. We end up visiting every single vertex in the graph. Then, in order to get the strongly connected component, we reverse the edges, and we run DFS on the reversed edges. And doing that, I'm going to do that in my head, but doing that, we get A, then we get reversed edge, we go to D, then C, and that's it. And then the intersection of these two sets gives us the strongly connected component, ACD. Okay? But again, it seems like a waste to visit all these other vertices, right? Every vertex in the graph. Let's go back to the graph. And it somewhat makes sense why we're visiting every single vertex, because if we look at the metagraph of strongly connected components, we see that ACD is a source. So from ACD, we could reach every other strongly connected component in the graph. And so when we run DFS on any of the vertices on ACD, we end up visiting every single vertex in the graph. So this is our worst case scenario, that we are basically selecting a vertex in this strongly connected source of a graph and running DFS on it. And that's why we get our polynomial time, we get our polynomial running time. It's because if we're always, in the worst case, selecting the source vertex of the metagraph, a vertex in the source vertex of the metagraph, then we're going to run DFS on all the nodes every single time. But what we want is to run DFS on a sink of the metagraph. If we knew that a particular vertex was in the sink of a metagraph, what would happen? What would happen? Let's run DFS on G. Let's run DFS on G, and so we highlight G, and that's it. DFS on G, we highlight G, and it finds all the elements in the strongly connected component. Then let's remove G. Then if we remove G, H becomes a new sink. Okay, let's run DFS on H without G there. And if we run DFS on H without G there, again, we only visit H. Okay, then we remove H, and now BEF becomes a sink of the metagraph. And so if we run DFS on BEF, then we run it. Then we start it on B. Then we reach E. Then we reach F, and that's it. We only visit the vertices that are in the sink of the metagraph. So what's our wishful thinking algorithm would be that if there is a U, a vertex U, in the sink of the strongly connected component of the metagraph, then what we would want to do is simply we want to do DFS on that vertex to compute the strongly connected component U. And we don't have to do the DFS on the reverse graph because we already know that because we already know U is in the sink. And so because we know U is in the sink, then we know all the elements, all the vertices that DFS U visit are part of its strongly connected component. And then we could remove we could remove this strongly connected component U from the metagraph and from the actual graph and rinse and repeat. Okay? And in total, we would only be running DFS on n total vertices. We would be using each edge only once. And so that would give us a linear running time. That is the insight of Kosaraju's algorithm. That basically, if we could calculate the strongly connected components for the sink of the graph, for the sink of the metagraph, and just go through and calculate it and go through and remove this sink and create a new sink and calculate the strongly connected component for that, and so on and so forth, then we would save a bunch of computation time. Okay? Now, the one issue is, how do we find a vertex in the sink of the strongly connected components? Okay? I mean, again, this graph here, the first idea is something to do with topological ordering, right? Something to do with what we've been discussing in lecture so much. But the one issue here is that this is in a directed acyclic graph. So would topological sorting work here? Can we obtain some implicit, something close to a topological sort of the metagraph without computing the metagraph itself? And the answer is calculate depth first search on G. Okay, so here's the claim. Let V be the here's the claim. If we calculate DFS on G reverse, okay, there is some vertex V, and V will have the maximum post-order numbering, then V is in a SCCS such that the SCCS is in the sink of the metagraph. Okay. So remember before how we said that if we ran DFS, the vertex with the largest post-order number is actually a source of the graph, and therefore it should go earliest in the topological sort. That's pretty much what we're doing here, except we are doing DFS on the reverse graph. Okay, so what does reverse graph mean? If a graph was a source, if we graph, let's write a graph V0, or actually just use A, B, C, D. A, B, C, D, D. So if a graph, if a vertex is a sink in the normal graph, this will be G, then in G reverse, this vertex like that, this vertex is now a source. How cool is that? So if this vertex is now a source in the reverse graph and we calculate DFS, then it will have the largest post-order numbering. But the issue is, what if this vertex isn't alone? What if this vertex, D, E, D, B, C, D, E, has a few more attached in a cycle? What if instead of a vertex, it's a strongly connected component? Well, the good news is that if this vertex was in a sink strongly connected component in the original graph, then it looks like this vertex is in a source strongly connected component of the reverse graph. Okay, and this will hold even if we delete strongly connected components one by one. We don't have to we don't have to recompute this function every single time. The post-order numbering holds. Okay, so I know many of you probably are uncertain. Let's go to an example. Okay, we're in the next video. We're going to go through an example, and hopefully that will quell some concerns. All right, so see you in a bit.